Okay, welcome back. Today we are going to continue our study of constitutive relations. In the segment just preceding this one, we looked at fluids. We looked at ideal and non-ideal fluids. We also looked at the notion of elastic, and in that context, we also looked at the notion of elastic and viscous fluids. We're going to continue with that along that path today and start off by talking about solids. We'll talk about the notion of elastic solids and really take this idea to some distance, and then we'll go on from there. Okay, so to start, we're sticking with constitutive relations, and we're now going to look at the notion of elastic solids. Okay, the notion is actually very obvious, right? It's a very natural one. It's very intuitive. So here we have our solid, and we are it deforms, right? So this would be as always, right? Reference configuration. Solid deforms. It's in the current configuration, the deformed configuration. Under the deformation, under the motion from reference to current configuration, we can compute the deformation gradient tensor, right? That's our basic measure of strain, stretch and strain. And the notion that we have of a solid is that when the solid is deformed, it develops a stress. Okay? So, going with that very intuitive idea, here's what we have, right? So we have the reference configuration of the body, the motion carries it to the current configuration, right? And the neighborhood of a point x goes to a spatial position little x, and associated with vectors that are scribed on the reference configuration, we get vectors in the current configuration through the tangent map f, okay, the deformation gradient. We know all about this. Okay, right, that is f. And then we have notions of stress. We have the notion of various stress tensors that are defined here. Of course, we know that P properly lives between the two configurations, but I'll just put it there. We have sigma, which properly lives here, right? The Cauchy stress. P is the first Euler-Kirchhoff stress. So I refer to this idea that solids, when deformed, develop stresses. So we have this very intuitive idea that the Cauchy stress right, sigma, can be written as some function, and let's suppose that function is g. It's a tensor function because sigma is a tensor, the Cauchy stress is a tensor. It's a tensor function of a tensor argument. All right? And from here, we know that we have the first Euler-Kirchhoff stress P, okay, P equals, we know it is equal to determinant of F sigma F inverse transpose. Okay, and given what we know about sigma, what we say we want to know about sigma, we are making sigma a function of the deformation gradient. It follows that P also can be written as some tensor function of the deformation gradient. All right? So this sort of dependence, when the stress depends upon the deformation gradient, is a very primitive notion of an elastic solid. Okay? In particular, this type of a model is what gets called as a green elastic solid. All right, and to make a bad joke, we're not referring to the color, we're referring to a mathematician there. Okay? So this is what we have as a very the sort of the first notion of an elastic solid. Okay? Let's work with this and see where it takes us. So let's apply this to the idea of the stress power. Okay? So consider the stress power, which we wrote as P internal, right, which is this integral over, I'm going to write it as an integral over the reference configuration. We've seen various forms for it. Let's consider this one. Okay, and let's go one step further. Well, before we go one step further, what we now have is that this entire integrand can be written as depending upon F only, all right, using our notion of a green elastic solid. Okay, so that's the internal power. What we want to think about now is that as we are deforming this body, right, we're deforming it. This is the current configuration. Of course, we've written this integral over the reference configuration. So here's the current configuration. We're considering the stress power just mathematically by integrating over the reference configuration here. Okay, but we know everything we need in order to construct this integral. Okay. So let us now ask ourselves the question, well, we have the power, but suppose we want to look at the actual amount of work done over some time interval, right? Because the power, of course, is a rate of doing work. Okay? So what we want to do now is, we started out with the stress power there. Let us now consider the work done. Okay? The work done W, right, which we are going to write naturally as an integral from, say, T1 to T2, okay, those are times, of P internal. Okay, let's just go with dt. Okay, and let's call this W1 to 2. Okay, with obvious meaning. All right. So of course now when we carry through what we know for the integrands, we get for the integrand we get integral T1 to T2, integral over the reference configuration GF contracted with F dot. dV. All right. Okay, so what this says is that we're integrating from T1 to T2, and we're computing the total work done. Okay, let's look at this schematically, and what I'm going to do here is schematically represent the deformation path. Okay, so I have time on this axis. Okay, and I have T1. T2, and on this vertical axis, on the ordinate, I am going to look at F. Okay, of course we know we can't quite do that on a two-dimensional board here because F is actually a 9-dimensional object, but this is meant to be schematic. Okay, demonstrative. All right, so we are going from T1 to T2, so let's suppose that along at T1 we have F1, and at T2 we have F2. Okay, now so the points of interest here are that and that one. Okay, now Of course, in this space, there is an infinity of paths that we can take between time t1 and t2, all right? Ending up, starting out at f1 and ending at f2. Okay, so that's path 1, that's another, right? And so on. Okay. What we want to know now is the following idea. We want to know what is happening with the work done here. Okay, so we want to know the following. So we are asking ourselves, is W1 to 2 invariant with respect to path? All right. Okay, so of course you understand how this works, right? If we take this first path, then at any time, at some time along this, we have f dot, right, schematically, and at some time along likewise along this path, we have a different f dot, and maybe to distinguish them, I'll label that as f2 dot and label that as f1 dot, right? That is what we would use in here, right, for each path. Okay. Actually, I realized that I should not call those f1 and f2 because that. Okay. Let me call this maybe path A, so I'd call that FA dot, and this would be path B, so I'd call it FB dot. Okay, and FA dot or FB dot is what I would use here, where I've marked the arrow just above the F dot in the integrand. Okay, and then as a function of F, I would compute G and go ahead and compute that integral. Okay, so this is the question we're asking: is W1 to 2 invariant with respect to path? Okay, all right. So what do you think? Is it invariant with respect to path? Always, unconditionally. Okay. In general, it is not, if you just look at that integral mathematically, all right? There is a condition under which it can be made invariant, okay? And to consider that, let's suppose we have the following. Let's suppose that our constitutive function for the green elastic solid, g of f, can be obtained as the derivative with respect to f, right, of some scalar function of f, right, where psi is a mapping. It starts out with GL3 because its argument is f, right, which is a general, which is a tensor, which is just a general linear transformation in 3 dimensions. It's mapped from there to the space of reals. Okay, right, because it's a scalar. Suppose we have this. Okay, what that implies then is that W1 to 2 is now integral T1 to T2 integral over omega naught of partial of psi with respect to f contracted with f dot, right, dv dt, and I realize I missed out a dt here. Okay, right? Okay, but then you look at this. This is just from the chain rule, given that psi is a function of f alone, right? What we have is that this is essentially psi dot. Okay? So our integral now becomes integral T1 to T2 integral over omega naught psi dot dv dt. Okay? Or, of course, this becomes, now we can do that time integral becomes becomes trivial. This integral essentially reduces to integral over omega naught psi at f, psi evaluated at f for the value t2 minus psi evaluated at f for the value t1, right? And of course, we defined f at t2 as being f2, f at t1 as being f1, right? And those are well defined. Integral dv. Okay? All right? Now, this is indeed independent of path, right? Because what we've written now is work essentially as a state function, right? It depends upon the state of the system, right, at whatever time of interest. Okay? So what we have here is now a state function of f, right? F may be a function of time, that's all right, but long as you know what f is at a particular time, that gives us psi, all right? And the difference between the psi's at different times or at different f's gives us the work done between those two states, independent of path. Okay? In calling that a state function, of course, I'm borrowing nomenclature from thermodynamics and without getting more formal about that. Okay, so if we have a solid that admits this type of a description, right, and furthermore, for one for which we are able to find a function, a suitable function psi, okay, we have our, in some sense, our most complete notion of elasticity. Okay, because this clearly means that as we deform the body, we deform the body at throughout the material. We have a deformation. We have a deformation gradient f at every point as a function of that deformation gradient. We have this function psi, right? And just by definition, there we are able to call this function psi the elastic strain energy density function. Okay, so I'm going to call psi function of f is the elastic strain energy density. You understand why it's called a density, right? Because in order to get the total work, we have to integrate over the volume, right? So it really is a density. Of course, it's obvious why it's called the elastic strain energy density, because F is the basic tensor from which we get all our notions of strain and stretch. Okay? So when we have such a model of elasticity, we have what is called a hyperelastic model. So this is a hyperelastic model of a solid, but equivalently we can do something like this for a fluid as well. Okay, and here's why. So this idea extends to elastic fluids okay, and as an example, let's consider the ideal elastic fluid okay, where we saw that we had sigma equals the pressure as a function of the density multiplied by the isotropic tensor. Okay? Right? Now observe that this can also be written as P because of the way we can write the mass density as depending upon the reference density divided by determinant of F, right? Okay, so what we have here is essentially our function g of F. All right? Okay, now since we said that the stress depends through the pressure upon the mass density, we can equivalently say that for this fluid, if we think of it as an elastic fluid and say that now as we compress it, it is slightly compressible, we can change its current density. We can also say, well, let's suppose that as we change the current density of this fluid by compressing it a little, it is also storing some amount of energy. Okay? And because it's an ideal fluid, what we can say from here is that let's suppose that there exists, let me use the same symbol psi, okay? And in particular, I'm going to make psi a function of F, just as we had there, but I'm going to say that this is some psi bar. How does it depend upon F? It depends upon F through some other function, which is a function of, okay, but that argument after all is just our current mass density. Okay, so we're saying that for this elastic fluid, let's suppose that we have this type of dependence. We have a scalar function, which is a sorry, I've got to call it psi bar, sorry, which is a function of the mass density. Okay, so what I have here is psi bar is a mapping from R plus, because the density, the mass density is a positive number, to R. Okay, so if we start out from here and then we say that, okay, our function sigma, which is now P function of rho times this, is essentially the derivative of psi with respect to F, right, times, oh, sorry, I need to have more stuff here. Okay, if we write sigma here as depending upon P as a function of rho multiplying the isotropic tensor, which is g of F, and we go through the calculations, what we are able to show is that P as a function of rho, okay, is equal to partial of psi, okay. What we're able to show is that P is a function of rho is equal to partial of psi times rho square. Okay, all right. So these sorts of results can be, this sort of a result can be shown. Okay, so this notion of a hyperelastic solid can be extended to a fluid, and to round off this segment, I just want to state that whereas we saw that if we have this hyperelastic model for a solid, right, so we have this idea of a strain energy density function, and if we are given that strain energy density function, we are assured that the work done in deforming the solid is independent of path. Okay? If we don't have a hyperelastic solid, right, so if we have that, getting back to the notion of a solid, right, if we have that P which is a function of f, is equal to this constitutive function, right? So right now we have green elastic solid, but we say that g of f is not obtained as the derivative of any strain energy function, okay, for any psi, okay? All right, supposing we say that we don't have any such psi that whose derivative with respect to f gives us g of f, okay? Then we have a hypoelastic solid, right? Or we have a hypoelastic model of a solid, okay? And with such a hypoelastic model of a solid, all right, in general, okay, in general, what we will see is that in general, W1 to 2, which is integral T1 to T2, integral over omega naught, P contracted with F dot, dV dt is not path independent. Okay? And this is important, because if you just say, okay, if you just say that P equals G of F, okay, and leave it at that, you can actually end up generating work in closed paths of this type. You can actually generate work in going from T1 to T2, right? Right, if you could take one path between T1 and T2, right? So you get here to F2 from F1, right? You may generate, you may have a certain amount of work in going from here to, from T1 to T2, all right? And if you take a different path, right? If this is path A and path B, depending upon the path that you take, you'll have different amounts of work, okay? Alternately, what you may say is that you could go in stress space then, right? You could, if I now plot up the stress and the deformation gradient in this manner, again, we know we can't actually draw these sorts of plots in 2 dimensions, but if you were to look at these kinds of work functions, what you would see is that if you were to go from some deformation gradient F1 to F2, okay, along one path, right, but then return along a different path, right, you will actually generate some amount of work, okay, even though you're working with what you believe is an elastic solid, okay. It is just that our notion of elasticity of a hypoelastic model, right, is not quite complete when it comes to this notion of reversible work and energy. Okay? All right, we'll stop here for this segment.